to record?
All right, go ahead.
Okay, so it's my great pleasure to welcome back Sam Coskey, who will talk to us about classification of countable models of ZFC.
Okay, yeah, thank you very much for the invitation. It's kind of a, I guess you're really, I haven't been to this seminar this way, but it seems like you're really taking advantage of, you know, the opportunity to get a lot of people together. So that's pretty cool. So yeah, so I'm talking about classification of models, countable models of ZFC. And I understand that in the seminar, you've already talked a little bit about the sort of descriptive set theoretic classification of countable models of arithmetic. So a lot of what I say is probably going to be the same as that, but I'll just sort of say it again briefly. But then I guess there are some distinctive aspects of ZFC as compared with PA, and I'll mention that. I mean, about which I know very little, but whatever I do know, I'll mention briefly sort of in the second half of the talk. So kind of overview. So I'm primarily a descriptive set theorist. And so whenever I see a diversity of constructions of something, so there are many constructions, of models of PA or ZFC, always countable models in this talk. If I say model, I mean countable model. And why that is will be explained later, why I'm so limited. Okay, and whenever I see something like that, I expect there to be a high complexity from a certain point of view. So, so high diversity often leads to high complexity from a descriptive point of view. So in both these cases, again, with a little bit of an asterisk, trying to classify all countable models of PA or ZFC or whatever should be highly intractable. And we kind of establish that or formalize that by establishing that it's as high of a complexity as possible within the domain that it's in. So, in the Borel reducibility hierarchy, which I'll introduce later, they have the maximum conceivable complexity. Okay, and then just, you know, note one difference that I was getting at a moment ago between, maybe I'm going too slowly, I should have made slides, between PA and ZFC is the existence of many standard models. So PA, one standard model, ZFC may have many. Okay, I mean, what I mean is some complete theories extending. Sorry, question?
Standard means transitive here for ZFC models?
Yeah, exactly, yeah. So, so some theories may have standard, you know, many standard models So it depends on the particular completion. I mean, I guess PA, it also depends on the particular completion, but anyway, depends on the complete T. Okay, so we'll just look at a couple of cases there. If you're interested in classifying those, the answer might be a little bit different than just classifying all possibly non-standard models later on. So the framework, the reducibility framework, probably everyone here has seen it quite a few times before, but just to briefly introduce how we kind of consider, how set theorist considers the class of models, class of countable models. I guess I can make a line here. Yeah, okay. So if M is a model of T, extending, which one should I do first? You know, ZFC, then if M is countable, we may assume its domain is the natural numbers. Okay, so M is just determined by the structure on N, which is just an epsilon. And so that would be an element of the power set of N cross N. Okay, so similarly, you know, for PA, then you have a plus of M and a times of M, and that's going to be an element of some big product. Okay, so in each case, this relevant space carries a product topology. So this is just the same as 2 to some countable power. Okay, so in each case, the space of countable models of T, so I'll denote it X sub T of countable models of T, inherits this product topology. Okay, and xt will be separable and completely metrizable. Which is Polish. Okay. So, and of course, it doesn't matter really that it's PA or ZFC. You know, it could have any countable language. And in fact, the theory T could even be a sentence of L omega 1 omega rather than a classical theory. Okay, so that's the space of points. And then in each case, any xt will carry an equivalence relation of isomorphism. So any given model will be represented in this space many, many times because you can always permute the natural numbers and get an equivalent structure. So the space xt always has, I mean, it has perhaps a number of different equivalence relations, but the most important one for today is isomorphism. equivalence relation, say isomorphism sub t. And so this pair, xt isomorphism sub t, man, bad handwriting, didn't work out so well, is kind of our stand-in for the classification of models of T. That's the structure of countable models of T, sorry. Don't want to offend anybody. And now you see why I always deal with countable models, because I really wanted this topology to be nice. I wanted a polar space. So we had to restrict just countable models for this. Though of course many people extend, descriptive set theory beyond just polar spaces, but that's okay. Okay, and then two such things can always be compared. So the Borel reducibility structure that I mentioned is a partial ordering on these things. So we can compare, any two isomorphism T and isomorphism T prime so isomorphism T is said to be Borel reducible to, or at most as complex as, isomorphism T prime if there exists a function from the domain from all the models of T to all the models of T prime, which is Borel.
Sam, excuse me. Do you see questions in chat?
Oh, I was not looking, but I certainly can. No, I guess I'm totally skating over some things. Is completely metrizable obvious? So what you need to know is that we have this big product space, like 2 to the n cross n of all possible binary relations, and then just the binary relations that satisfy the theory T is an arithmetic subset of that, and all you really need is that it's Borel, and then right. So I guess I should say it has a compatible topology that's completely metrizable. I don't know if, I guess I should not say that that particular topology is completely metrizable. Thank you, yeah. So that's not right. So it has a separable and completely metrizable topology with the same Borel sets as the product topology. So all we really care about is, I was just writing this word Borel. Yes, I guess so. I mean, it's a standard, a standard theorem. Yeah. So right, so at the end of the day, we just care about the Borel set, so that gives us a lot of flexibility, and we just care about the Borel sets and the Borel functions. So there should be for isomorphism T to be reducible to isomorphism T prime, there should be a Borel function of the domains, and it's kind of classifying models of T being classified by models of T prime. So M is isomorphic to N, to models of T, if and only if f of M is isomorphic as models of T prime to f of N. Okay. So this classifying function, it sends isomorphic models to isomorphic models, and conversely, any two isomorphic things that it spits out came from isomorphic things. Okay. So this less than or equal to sub b is a really complicated partial ordering on all these classes of models. I'm not going to get into all the different kind of hierarchies, sub-hierarchies, and different rungs along that partial ordering, but just for the very, very first things that we need to know. So classifications, maybe, among other things. So smooth, Borel complete, or in between, or they can actually be a bit to the side in principle, but I'm going to skate over that for this talk. So smooth is kind of you should think of as the lowest end of the complexity hierarchy. So this means that isomorphism T is reducible to, if on the right-hand side, rather than isomorphism T prime, I just put the equality relation. So just the identity equivalence relation is reducible to equality relation on some Polish space, like 2 to the n. Here, this map F would be behaving as complete invariance for the classification of models of T. It would mean that f of m is just some infinite binary sequence, which you can just think of as a real number or a sequence of zeros and ones, a sequence of true or false questions that completely characterizes M up to isomorphism. Borel complete, this is just an abstract thing. So for the moment, it just means that for all T prime, isomorphism T prime is reducible to isomorphism T. So isomorphism T is Borel complete if no matter what you throw at it, it's maximally complex. Okay, and this exists. There is a maximum complexity. So this is maximum, at least among these type of classification problems. It's not maximum over all equivalence relations. And intermediate, and here's where there's many things, okay? So a complex structure. Okay, one of the things you probably have heard of a few times that exists here is E0, which was sort of invented for this purpose. The first thing that's shown to be non-smooth. So E0 is on 2 to the n, and x is E0 to y, oops, just y, if and only if there exists n for all n greater than or equal to n, x of n equals y of n. So eventual equality of binary sequences. We'll mention that one later. So just some examples of things that are Borel complete. Examples of, well, I guess I should do them all. Smooth. I always do the same example here. T equals the theory of torsion abelian groups. So the countable ones, they're just the rationals, group of rationals, the proofer groups and products of those. So they can be classified completely by in a natural way. Examples of intermediate. Let's see, the isomorphism of finitely generated models of T. So T containing PA. This is the classification of finitely generated models of T. Okay, and examples of Borel complete. So problems which are utterly intractable, the classification of T contains PA. We'll talk about that one in a few minutes. And also T equals, I guess, classification of T equals the theory of countable graphs is usually the one that people talk about. Countable, even countable connected graphs, or T equals the theory of countable linear orders. Just arbitrary countable linear orders is as complex as possible. So that's the framework of classification. Any questions here? Haven't monitored the chat properly, but it's empty. So again, I never know if I'm boring people or skating over too many details. But so the theorem that I understood may have been presented here before by Roman. So 2009 with Roman. So we, in this paper, we addressed a number of different classes of models of PA, countable models of PA, at least a few, as well as classifying automorphisms and classifying extending pairs. But the only theorem that I want to mention today, I guess I already mentioned the thing about the finitely generated models, but if you just look at arbitrary models, it's Borel complete. I guess I mentioned it right there as well. I got ahead of myself. Okay, so if T contains PA, isomorphism T is Borel complete. So as complex as possible. And it's not very hard given some facts in the literature. So how does this work? So the first concept is a minimal type. So we were going to use Geifmann's minimal types and minimal extensions. Okay, so a type P of V is minimal if it is one. So I'll define minimal type, then I'll state a couple facts about it, and then I'll see why those couple facts about it imply what we want. So unbounded, that means for all, I guess a type P, what over a model. Okay, so it's unbounded if for all A less than V is in P. And it's indiscernible. Which means it's realizations. And when you realize P and an extension of M, you always get order indiscernibles. So if A, B are increasing sequences of realizations of P of V in N extending M, then, N with A is elementary equivalent to N with B. They satisfy the same formulas. Okay, so Geifmann showed any M admits indiscernibles. Admits minimal types as well as indiscernible type. Minimal types. Okay. And then the next step is what do we do with minimal types? So given M, P of V minimal, and I, a linear order, Geifman constructs a canonical I model. Relative to the P. M of I. And M of I is generated over M by an I sequence of indiscernible realizations of P. So for me, I will be a countable linear order, but I suppose it doesn't matter initially. An I sequence of realizations of P. And it satisfies the I sequence, the generators are order indiscernible. And from the isomorphism type of M of I, one can recover the order type of I. Among many other useful properties that I don't use. But so essentially, thus the construction, the map F, which from a code for a linear order produces a code for M of I, is the Borel reduction we desire. So we're trying to show that these models are Borel complete. We know that linear orders up to isomorphism are Borel complete. So we're just going to reduce something known Borel complete to this class of models. Now to show that something's a Borel reduction, there's a by implication up there. So I lost it, I suppose. Oh yeah, here it is. You have to have that two linear orders are isomorphic if and only if the two models they generate are isomorphic. And that's just this A and B. So, you know, for this direction, we use A, and for this direction, we use B. And that's sort of all we said in that 2009 paper. So we also sort of offhandedly mentioned that this should, you know, work for ZFC, or maybe we didn't mention it, but we probably thought it. So I thought that'd be a good project for a student to check that it actually does. First of all, that the proof actually works because we didn't repeat all the details from the literature. And second of all, that it works even if you substitute in ZFC instead of PA. So that's that turns out more or less true. If T is a theory of ZFC, but it's also got to satisfy global choice, then, so just make it really easy on ourselves, then isomorphism T is Borel complete.
Can I ask a quick question, Sam?
Please. Yeah.
When you say it satisfies global choice, do you mean it contains v equals hod, or do you mean you have an extra predicate for the global well order? Or does it matter?
I meant the second thing, but I don't know if it matters.
Okay, thank you.
Yeah, you probably could tell me better than I could tell you. But yeah, essentially what I wanted. I mean, I guess it doesn't matter. I guess either way would be fine. All I
Well,
want
yeah,
is to
because
be
if
able
you
to,
have it with the predicate, you should be able to get it with like things that satisfy v equal hod.
right. So yeah, the way it's going to be used, the GC, is just that we're going to, you want to like generate a model. So you need to have Scullin terms. So you need to pick a witness for an existential formula.
Sam, since we're in questions, there is something in chat.
Oh, great. Is obviously F is Brill. Well, you see, that's one of those things that maybe we did. I don't remember. We didn't think about too greatly, but yeah, the construction, I guess, you know, it's one of these sort of Scullin-Hull type of constructions. So that can be executed in a Brill way.
Well, I think that the philosophy here is that wherever you do something that doesn't require the axiom of choice, and clearly you don't need any choice for doing these Geifman constructions. They're very explicit.
Right.
Sure. Okay. Thanks.
Yeah, I mean, you need something. You need, like, you know, dependent choices or something. But yeah, it's very very explicit modulo, that sort of. So and so we just need to copy that. That's where this GC comes in. I don't have any other substitute for that. So I even wrote that here in my notes, but we just said it so much. GC is used for Scullin terms. It's not clear that it's needed. I mean, I don't know how anyone, I don't know a model of a proof of this theorem if you take away the GC. So I'd love to hear about it, but I don't know even how to get started. Okay, and so the proof, as sort of promised, is similar to the above. Okay, so every model of ZFC, you know, contains an omega, which is a model of PA, and we just kind of work inside there. So, but with omega hyphen inserted in many places. I will say more than just this, but this may satisfy you, or it may not. So it satisfied me, and then I tried to write that in the paper, and it did not satisfy the referee. So we ended up writing quite a lot more details than in 2009, you know, mostly taken from Coskey Schmerl textbook or Chinlock Wang's notes on minimal types. But essentially, it's true that it's just the omega hyphen is inserted. So, for example, you know, a type, I don't want to spend too much time here. P of V is an omega type if V is in omega, is in P. It is omega minimal if, so again, minimal was unbounded and indiscernible. For us, we just want unbounded in omega and indiscernible. So omega minimal will say, for all alpha in omega of the model, alpha less than V is in P. And indiscernible is the same. So just kind of working inside the omega of M. And so then we again check that such types exist, copying Geifman's arguments or similar. And we again construct M of I. M of I, okay, and we needed the Scullin terms. Okay, and we again prove, you know, A and B. so what were A and B? The A was that you have indiscernible elements, so that means an automorphism of the generators would extend to an automorphism of the M of I. And part B is saying that we can actually recover the order type of I from the structure of the model M of I. So indiscernible and ability to recover I from M of I. And that enables us to write out the proof as before. So I don't have too much to add about that, but we do have at least some details kind of, sketched out.
Sorry, Sam, can I ask one question?
Yeah.
Is the omega of this M of I the old M of I from the PA case then? I mean, do you get that old model of PA that you would have gotten in the first construction when you do the model of ZFC here?
I don't know. I feel like I thought about that at some point and I couldn't answer it, but maybe it's obvious. I guess, you have these extra terms, and I don't know what kind of they say about omega. I mean, yeah, I don't know. Does the question make sense? Right, we have this theory that extends ZFC.
Those things that you could say about omega are just those things that could already have been said about any omega of any model of ZFC, right? I don't think the type can say more about omega. Is that
right? That could, like, the question is, like, can it say more about the omega of M than the omega of M with plus and times can say about the omega of M? I don't know. I'm not sure. Maybe after we can talk about it.
Okay, thank you.
I would need help on that one. And maybe it's obvious, but I don't know. Okay, so yeah, other questions before I move on to well-founded models. So I realize I'm a bit vague with the A and B, but especially B, but it's not fundamentally different from the PA case. So that's why I sort of didn't spend too much time on it until the referee demanded. So yeah, this is sort of the new thing, and I have very little to say about it, but I feel like there's some questions here that, and I've kind of stopped researching this area, but I feel like there's some questions here that a lot of people would be interested in, and so I'm sort of happy to be able to advertise. So the above proof obviously uses ill-founded models. It's the same as the proof for models of PA. So exclusively ill-founded models. Because we're stuffing things into omega. So, many people have studied the different possibilities. So Inayat and many others have shown, given conditions on a theory T or examples of a theory T that have various numbers of well-founded models. Have shown a theory T of ZFC may have no well-founded models. It may have a unique well-founded model. It may have finitely many other than one. It may have countably many. It may have L1 many. It may have continuum many. Standard well-founded models. Okay, so in situations where there's just a few, then classification isn't very interesting. But in situations where there's uncountably many, then we can start to ask, well, are there smoothly many or non-smoothly many? Is there Borel complete many, etc.? So, so now the object we want to study is X, I'll just call it WFT, equal the subset of XT consisting of well-founded models. Might be empty.
Sam, can I ask a question?
Yeah.
What about the intermediate case of omega models that are ill-founded? Have you thought about that? Because it seems what you said before assumes an ill-founded omega. What if it's well-founded up to some? Or no,
sorry, an omega model that's ill-founded. Oh, sure. Yeah, I didn't think about it.
In that case, you don't know also. Okay.
Yeah, that seems that. I mean, that seems worth considering. Because these things up here, they're not only ill-founded, they're not omega models. So yeah, that'd be awesome. That's all I have to say about that.
Cool, thanks.
And you know, isomorphism WFT, the restriction of the isomorphism relation. So what can we say about this? Again, not so very much, but maybe I'll call it a proposition. Isomorphism WFT for any t is never truly Borel complete. Okay, and well, okay, I guess I have a caveat. So note X WFT may be non-Borel because you're cutting away the well-founded things, and that's to say well-founded is a pi11 thing to say. So this may be non-Borel. So from that point of view, it's not very good from the Borel reducibility theory, but you can still ask whether there are Borel reductions to it. In other words, if the function f just happens to have range contained in that set, that's fine. So we can still ask whether any given equivalence relation you like is Borel reducible to isomorphism WFT. That doesn't, because the Borel function, it has a finite domain over here, some standard Borel space that's the domain of E, which is its range may be contained in X WFT. And we can also ask whether, as we'll do a little later, isomorphism WFT is reducible to some other equivalence relation E, but where Borel is replaced by something a little weaker. So often people put absolutely delta 1, 2 in there, and it's still somehow like reasonably definable, but it doesn't care about pi11 sets, so it sort of gets around the weakness that dealing with Borel functions has. So that's kind of just the caveat in this whole entire section of the talk. But anyway, so when I say it's not Borel complete, I mean nothing Borel complete reduces to it. And this is sort of trivial from a certain point of view. The reason is nothing well-founded is ever Borel complete. So the boundedness theorem gets in the way. So let's see, where did I write that? So the idea is, suppose some Borel complete, like graphs or groups or linear orders, isomorphism relation reduces to it. Okay, then all these models in the set of well-founded models of T, they have a rank. So you could use many different ranks, but in particular, you could use the order type of the ordinals of the model, O of M. So then, f of x, let's see, every f of x has an ordinal rank O of M, which is the order type of the ordinals of M. And by the boundedness theorem and descriptive set theory, this Borel function must take values in a bounded set of ranks. So this is just never going to work. Range F is bounded in rank. Okay, but isomorphism WFT restricted to any bounded rank, I don't know how to denote this, restricted to just having rank less or equal to some particular countable ordinal is actually always a equivalence relation that's Borel as a set of pairs. Sorry, I haven't been monitoring the chat. Okay, we'll look at that one later because it's long. Thank you, Heather. So this is Borel as a set of pairs. Well, so I guess Harvey-Friedman showed that, or Friedman and Stanley showed that. While isomorphism, this Borel complete thing, is actually non-Borel as a set of pairs. Hello. So that both of those facts are Friedman and Stanley. They're old, I guess. And so then you can't have a Borel function reducing a non-Borel equivalence relation to a Borel equivalence relation. Okay, so that's the first observation. We're never Borel complete if we restrict to well-founded models, but you could be kind of pseudo-Borel complete, as I said a minute ago, if you allow weaker reductions. And so there, I don't know if that can happen. So I'll just put it as a question. You know, could isomorphism WFT be pseudo-Borel complete with something like absolutely delta 1, 2 or some weaker than Borel reduction function. Okay. Okay. So what, we go to 4? So the last example I want to give is that so that's basically the best I can say. So can at least be non-smooth. Okay, so I guess I have an intermediate example, but if it has exactly omega 1 many equivalence classes, then of course that's sort of to the side of smooth. But let's do one that has continuum many equivalence classes and is still non-smooth. So the theorem is I guess it's a theorem, if T is the theory of M of G, where M is a transitive model, countable transitive model, of ZFC, and G is a Cohen real, then isomorphism WFT is not smooth. Okay, and it probably should be much higher than just not smooth, but that's what we can say for now. So proof outline. Okay, so here we're going to use that E0. It's the first non-smooth equivalence relation. So we'll just recall that. X is E0 to Y if and only if X and Y are almost identical sequences, and E0 is not smooth. Will you let me have a little time? Come up and see you soon. Okay, see you soon. Okay, so next define E equals E Cohen on the set of reals in the real universe V that are Cohen generic over M. Of M generic Cohen reals by G1 is E to G2 if and only if M of G1 is M of G2. So we show that E0 is reducible to this E Cohen, and then below E Cohen is reducible to isomorphism. Okay, so E0 is reducible to E Cohen. So I guess clearly if two generics differ, if they're almost equal, then they're going to give rise to the same forcing extension. So if you take E0 and restrict it to just the Cohen generics, so the statement that any two E0 equivalent G's give rise to the same M of G is just saying that E0 restricted to the Cohen generics is a sub-equivalence relation of E. Okay, and this is enough. So that's clear that it's enough is sort of standard descriptive set theory knowledge about E0, that when you take E0 and restrict it to a comeagre set, which this is, then it still has the complexity of E0. And moreover, when E0 is a sub-relation of some countable Borel equivalence relation E, then E0 is actually Borel reducible to that E. So it's not a direct proof here, but it is like well known after this first observation. And so then for the second claim, this one is more direct. So given G, build a code for M of G. Okay, so this can be done in a Borel fashion just because the forcing relation is, so definable. So It's arithmetic over M. So from G, we can build a code for the model M of G. Okay, and so then, of course, well, if G1 is equivalent to G2, then M of G1 is actually physically equal to M of G2, which of course implies they're isomorphic. And conversely, if M of G1 is isomorphic to M of G2, then they're transitive. So this is, I mean, M, the original M, these are codes, but the original M was a transitive model, so isomorphism implies equality. So that's the definition, that G1 is E to G2. Okay. So that is the conclusion of that. And it's a bit weak because we're just getting that, you know, this relation is not smooth. So this proof direction can't really take you much farther. So Ian Smith recently showed, he analyzed this E. I mean, you know, we know that it's above E0, but is it any higher than that? He showed that we're probably not going to prove that anytime soon. E is hyper finite, which conjecturally is equivalent to hyperfinite. So conjecturally is reducible to E0. I'm not sure if people believe this conjecture, but it's certainly not known. Conjectured, this implies E is reducible to E0, so that this entire proof would get you no higher in complexity. Smith also analyzed the same equivalence relation, but for random reals. And he also showed,
I'm sorry, can you say can you say what's hyperfine?
Yeah, okay. No, it's in quotes. I don't need to say what it is. So it's
tiny quotes, I don't care.
It's a union of En where the En are nested equivalence relations, and they are all hyperfinite, which means reducible to E0.
All right, thanks.
Yeah, so it's like it should be the next level or whatever, but it's no one's able to prove that it's the next level, and conjecturally it doesn't actually increase complexity. So he also showed E random, the same equivalence relation but with random reals, is actually higher in complexity, is above E0. So I guess if you just, I didn't really check it, but if you just run the same theorem but with the theory of G, F of G, G a random real, then you would get a little bit higher for isomorphism WFT, which is nice. So that'll happen more recently. Okay, so that's the end of my material. Thanks again for the opportunity.
Okay, thank you, Sam. So now we awkwardly clap.
Yes.
And now we ask questions.
Yeah, I have oh, you go first, please. Yeah, okay, I'll go start again. Yeah, it's sort of a general question. As I remember it, you have Borel determinacy, and that meant that in the Borel hierarchy, the standard Borel hierarchy, you only had the delta degree and the complete degree.
You're asking the wrong person, but yeah, probably.
Okay, and I think wage determinacy is enough to get that, I think.
Okay.
Okay, and also I remember there's a question was, people were asking, was in general, the situation where there are truly intermediate degrees is actually the unusual one. And one case was, of course, with post problem, you do have intermediate degrees, but then you have Aslanov's theorem, which says that it's rather an unusual situation, et cetera, et cetera. I'm sort of quoting from a paper of Steve Simpson's years ago. But so how are you in the Borel universe here and, getting these intermediate degrees?
Gotcha. Yeah, so it's, they're not really wage. So going back to it's really kind of a surprising departure from intuition. But yeah, so going back to the definition of Borel reducibility, we have an equivalence relation is reducible to another equivalence relation. So this is a set of pairs, and this is a set of pairs. If there's a function, and the function is just a unary function, it's defined on points. And so this creates a hierarchy that has little to do with wage degrees. Well, it has little to do with the Borel hierarchy, because the function itself is Borel, so it can kind of trump any, right, any, if this one is sigma 0.5 and this one is sigma 0.8, you could still have the higher number being reducible to the lower number because the function itself could hide a lot of complexity. When you get up to the projective hierarchy, then, well, the functions are Borel, so they do have to respect the projective hierarchy. So you can't have like a pi 1, 2 thing reducing to a pi 1, 1 thing. But by and large, the equivalence relations here are all sigma 1, 1 or better. So the only problem occurred down when I was looking at well-founded structures, and then we're not talking about wage degrees, but just going a little bit beyond Borel in the projective hierarchy.
Oh, thank you.
Can I ask a question?
Mm-hmm.
On the arithmetical side, are there any results about theories weaker than PA, classifying models of, for example, Pressburger arithmetic?
That's a good question. I don't know of anyone directly addressing. So,
Okay.
I mean, of course, any model of PA is a model of something weaker than PA, but if you could say something special.
Yeah, I think Pressburger arithmetic, it counts as a mild arithmetic because you can pretty much have a good handle on what the models look like. They're rather algebraic. So one's intuition is that they should be classifiable. But I was wondering if anybody has shown whether that intuition is right. Yeah.
Doesn't that contain classifiable? Oh, I see. Right. So a model of PRA.
Yeah.
The classification is. I mean, right. Every model of PA is a model of PRA, but you're saying that they can be. I guess they can be isomorphic as models of Pressburger.
Maybe if we go back to linear orders, you said the linear orders are like the most complex, right?
Right.
But if we limit to particular kinds of linear orders, presumably you can get a good. I don't know whether.
Right.
I mean, that's probably.
Ali,
yeah.
But in that paper with Sam, we have something about recursively desaturated models, and then they are in this strange category of E set, and that's where you can classify isomorphism types by their standard systems. And so for recursively desaturated models of Pressburger, the same holds.
Okay.
So that's they are not quite as algebraic as they would seem. So they're certainly above E0, but perhaps what the exact status is, and no one really has looked at it. But we have recursively desaturated models, and they go above E0.
And does the result apply to recursively saturated models of theories weaker than PA, or?
Yeah.
This is marker, right? There's
Sorry?
a marker.
Yeah, there is a theorem of marker. We proved actually something that in case of that marker has a general result of.
But because PA has the very is very powerful and it can build these minimal types, so it would be nice to have results which indicate that there is something special about this result of yours. The fact that models of PA are wild, countable models are wild, and that if you maybe look at theories are weaker than PA. Maybe it's, I don't even know what happens to what happens if you limit induction to a particular finite level, like I sigma 1, for example. So it seems to be a big wide area of open field research. Okay, so it hasn't, my understanding is that if I hear you correctly, no work has been done in that direction, yeah?
Right, I'm aware of it.
Okay. And if you don't mind, as long as I'll make a quick other question just to, so I will finish my turn. When it comes to models of ZF, well, models of set theory, whether we have global choice or not, so you talked about the fact that if we look at well-founded sets, well-founded models, you know, with what the situation is rather, let's see, I think you said, right, so basically the main problem is that they're not even, the well-founded models of a particular completion are not even Borel because it's pi 1, 1, and then the contrasting feature is that if you look at well-founded models, they come, countable well-founded models, they come up, they have each a countable ordinal height. So if we fix a particular ordinal height, O of M, to be fixed ahead of time, then we get a Borel.
Yes.
And there maybe, do you know what you can say about that?
No, I don't, and I'd like to. I mean, the examples down here are so sort of poor. I mean, I shouldn't claim that these are the only examples, but the examples that I know about, okay. I know so little about. But yeah, I mean, you'd like to say that, if you classify just the well-founded trees of ordinal rank exactly alpha, then that's a well-known benchmark in the Borel reducibility hierarchy. It's called F alpha or whatever, or F alpha plus 1 or something. So it'd be nice to be able to hit those markers.
Yes. Yeah. Okay.
Yeah, I just haven't.
Yes, yeah. It seems.
I haven't really done a lot, as you can see, and so yeah, I don't know how.
And before, or I should say, maybe after your work with Raman, has there been any other papers close to this subject, models of either set theory or arithmetic?
You've asked me this before, and I think still I haven't.
Okay.
Yeah, I mean, I've been a little bit out of commission with COVID, but yeah, I haven't noticed, haven't been informed or seen too much.
Okay.
Yeah.
Thank you.
Yeah.
Right. So I
thank you as well for inspiring some of this work.
Yeah. So the paper didn't inspire anyone, or maybe it did inspire people, but it's strangely nothing much more can be said than we said, and in particular there's this problem about finitely generated models of PA, and we only proved that it's and thanks to Jim, who provided a key lemma that that relation is not smooth. But we couldn't pin down exactly where it sits in this Borel hierarchy of relations. So, so it's everything around it is quite open.
I see.
Were you able to show that for the finitely generated that it's not complete? Or that's not Borel complete?
No. Oh no, yeah. yes, definitely, yes.
It's
because it's Borel.
It's Borel. Okay.
It's below this. It's below E infinity. Is that right? It's below. Yeah, it's a reducible to a countable Borel equivalence relation. So it has a bound that way, but then inside there's a lot of complexity. So yeah, I mean, I don't think we've said everything that can be said. I just think not too many people have worked on.
No, but I know some people who did.
Okay.
Bob Andelichkovich put some thought into it, and then people who know about problems with Borel hierarchy said, but it seems to me that some specific facts about PA that would be needed there, and we couldn't quite figure some group actions on finitely generated models of PA, and we couldn't quite see how to do that.
I just remembered there was a paper by Emil Jezabek on models of Pressburger arithmetic, where he classifies, if I remember correctly, rigid models of Pressburger arithmetic, and they were of size at most continuum, as I remember. And this is a rather recent paper. So it makes me wonder if the techniques in his paper help to classify, or at least shed some light on the classification problem for models of Pressburger arithmetic.
Sure, yeah, whenever you see a mathematician in their native domain working to classify something, then probably step in and it might be trivial, just to translate what they're saying into the descriptive context, but it might be non-trivial to really show that it could be done, in a Borel fashion or whatever. So there's almost always at least something to say.
Yeah.
So that sounds good.
Yeah.
Okay, Cameron. It's Cameron. Cameron Ken had a question.
Well, it's not a question, it's a comment that Boise, where our speaker is, right, is one of the answers to a great trivia question. What are the 6 state capitals that were named by French explorers or French priests?
Okay, yeah.
What are the other 5?
It's French.
Boise is one, meaning woody.
Yep.
Montpellier in Vermont, Baton Rouge in Louisiana, St. Paul, Minnesota, Des Moines in Iowa, and the other one is, the hard one is Pierre. And Little Rock was originally called Petite Roche, but it got anglicized.
So Ken, are you saying Boise is actually pronounced Boise?
Boise.
Boise, I see. Okay.
No.
It had been, that's right, yeah.
And what's your daughter's name?
Who?
Sam's daughter's name.
So it's my son, and he's
sorry about that.
He wanted to have long hair, so it's been quite a challenge, but we've dealt with it.
So can we say hi to him?
What's that?
Can we say hi to him?
Oh, I shoot him away.
That was probably...
So he has changed so much, Sam. It is crazy. I did not recognize him.
I know.
How old is he?
He's almost 6.
Oh my goodness. Maya wanted to see him very much, but she ran off to the playground.
Oh, okay. Yeah, they got along well. So
it was fun.
It'd be awesome to play again soon.
She said to say hi to you from her.
Hi back. Yeah. That would be great.